Hello everybody and welcome to my short tutorial series on collision detection algorithms in games. In these videos I'll be covering 4 different algorithms, explaining how they work, giving a rundown on the benefits and problems with each one, and showing you how you can implement the algorithm in your own games. I'll be posting all of the code from this entire series to GitHub, and I'll leave links in the description along with any other resources I may mention during the videos. I would strongly recommend watching the videos through and writing the code for yourself though, so that you understand the principles. Before we begin, I'm going to make a few disclaimers. To start with, I'm not a professional. I'm fairly new to coding altogether, and so the implementations I show you won't necessarily be watertight. That being said, I have gone to a lot of effort to understand the algorithms I'm presenting, and I've tested my implementations thoroughly, so you can expect a good quality there. Secondly, and this is a reasonable distinction here, I'm only going to be showing you intersection detection algorithms in these videos. Functionally, these can easily be turned into collision detection, and if there is call for it, I may add another video showing you how. I'll be doing all of my code in Java. I hope my explanations will translate, and I'll make sure to explain everything as I go along. I'm no artist as well. I'm going to be doing rough sketches to demonstrate the key aspects of the algorithm as we go along. These are my best attempts. I'm sorry. I've made very few attempts to optimize the algorithms as we go through. In a few cases I've actually left them deliberately open. I'll discuss the optimizations, but I would like the code to be as generic as possible to give you the freedom to fit it to your situation. I will say, I'm going to be describing the algorithms in 3D, but they are all equally applicable in any dimensional environment. All you need to do is add or remove the dimensions in appropriate places. And finally, this is not a Java tutorial. I assume that you'll have a fairly good knowledge of how to code, have some sort of backbone project already, and that you understand the basic principles of rendering in your chosen dimensions. I will gloss over all of the basic coding and focus purely on the algorithms. Okay. Now that that's done with, we are going to hop into my testing world so I can show you the 4 algorithms we'll be using. The order you see them here is the axis aligned bounding box, the greatest radius sphere method or the bubble method, the hyperplane intersection algorithm, and finally the Farabi collision algorithm. In this video I'll be explaining the first 2. Next video I'll cover hyperplane intersection, and finally I will show the Farabi method. Before I start coding anything though, these algorithms do assume a few things from your program. For a start, I'm going to be using a class called entity. This will be the model that you want to check for collision. You should be able to extract from this model the vertices, the indices to read them, and the normals to each triangle, or at the very least be able to calculate them on the fly. You should also be able to get the entity's position in the world space along with its rotation and scale. I assume you're able to generate the standard transformation matrix for the entity. I will use a maths class to do this. If you're unsure of how to do it or what it is, there are a lot of tutorials online, but I'm going to include it in the maths in the code that I upload to GitHub. I'm also going to assume that you have a standard, well-written implementation of vectors and matrices. I'm going to be using the LWJGL collection for this. But if you don't have or want to use these, then I'll recommend that you either write your own or go looking online. There are a lot available. So assuming that you have all of that down, I'm going to start work on my first algorithm, which is the greatest radius sphere, or the bubble method. How does the bubble method work? If I take an arbitrary shape, like this, defined by a set of vertices in model space, then I measure the vertices distance from the origin. I can see the furthest point that extends from the shape. In this model here, it's this dot at the top, and I'll draw a quick circle to demonstrate that no matter how you orient the shape, this dot is always going to be the one furthest from the origin. The only time, in fact, that the radius of this circle will change is if the scale factor of the shape changes, in which case all we need to do is multiply the radius by the scale factor. To determine a collision, what we do is we define any two shapes with these circles, and then just measure the distance between the two origins. If the distance between the two origins is less than or equal to the sum of the two radii, then a collision has occurred. Otherwise, we can be certain that there's no way the two shapes intersect at all. As I'm sure you can tell, this algorithm is most effective when the entity approximates to being a sphere. We have all that we need to implement this now, so I'm going to take you to the code. So we're here in my workspace. I'm going to be showing you how to implement the bubble detector algorithm now. The first thing I've done is I've created two empty classes. One is my collision detector class. That's going to handle all of my collision detectors. And secondly, the bubble detector class, which is the one we're going to be working with today. So in the bubble detector class, what we're going to want to do is create our detection. That's going to be a method, let's call it public, a static method, just returns a boolean for does collide. Now that takes in two entities. We're going to call them primary and secondary, although it doesn't actually matter the order that they come in. And I'm going to, whilst I'm here, make another method called private static. This one returns a float, and that finds the furthest point, like that. And that just takes in any entity E. And I've just said fid there. So find the furthest point. What we want to do, for a start, we get every vertex from the entity. So in my case that comes in as a float array. Get the vertices. I'll want to define the longest distance, so float longest distance. Terrible spelling today. And we'll start that off as 0. Just add to that as we go along. I'm going to create a quick for loop here, so for less than vertices.length, and because I'm in 3D I want to divide that by 3 and just instantiate it through. Create, just for myself here, a root, so that's going to be where we are in the vertex array, and I'm going to create a vector to define each vertice. So that's going to be vector3f vertex, and that's a new vector, and that's just defined as vertices root vertices root plus 1 and vertices root plus 2. So that's just a vector with each 3 on there. And find out what I've done wrong. And forgot to put a square bracket. No harm done though. What I will say is, as I said in the video earlier, there's no way that this radius ever changes except for with scale. So the fact that I'm calculating this with every call is a bit redundant. There's no reason that you couldn't just attach the furthest distance to each entity even as you load it into the game. It's a very, very small calculation. For now though, I'm just going to keep it as it is. This is just optimization advice if you're doing it yourself. So next we take the distance from the origin to the vertex, and that's going to be vertex.length. Very simple. And if that distance is greater than the longest distance, then we just set the longest distance to be equal to the distance we got there. When we're done, we just return the longest distance that we found, like that. Now we've got that in, everything else comes very simply. All we do is we create a float for the furthest primary equals find furthest point primary, and then, and you can't forget this, we have to multiply that by the scale factor, like such. So So that will tell us the radius of the scaled object. We then just repeat this for the secondary. So check in secondary instead of primary there, and just do that for all of these. So these are our two radii. Finally, we need to do the distance between the origins, and that's going to be very simply typing too fast here. That's going to be the difference between the position of the first entity and the second entity, and we just take the length of that vector. So what we have here is the two radii and the distance between the two origins, and like I said before, all we need to do to calculate if there's a collision is the distance less than or equal to the sum of the two radii plus furthest secondary. And I'm sure I've misspelt something in there. Yep, we call that distance to origin. I'm just going to hop into my collision detector class here. I'm going to create a public static boolean bubble collide. That just takes entity primary, entity secondary, and we return the result of the bubble detector. Does collide primary and secondary. And that's really all there is to it. Now if we call from the game class the bubble collide, it will tell us if any two entities have a collision. So I promised I'd show you a second method in this video, and that is the axis aligned bounding box. This is probably the most popular simple algorithm that I've found, and I'm including it because collision detection hardly feels complete without it. The principle is very simple. For shape A and shape B, you take the box that most snugly wraps the shape and use logic to determine if box A and box B overlap at any point. If they don't, the objects definitely don't intersect. To make the box, it's very simple. We just take the maximum and minimum values of the coordinate positions of each vertex along each axial plane, like you can see here. To determine an intersection, all we need to ask is when do any two given lines intersect, and that will be when the maximum value of either is larger than the minimum value of the other, but the minimum value isn't larger than the maximum as well. And that looks a little bit like this. That's a little bit wordy, so we ask when do they not intersect, and that's as simple as when the maximum value of one line is less than the minimum value of the other, or vice versa, like this. If you're finding this a bit confusing, I'll explain some more later, but all you need to understand from this is that a square is just two lines we need to check for intersection, and a cube is three, and we know that the shapes overlap if every single line has an intersection on it. The shapes don't overlap if at least one doesn't. Now we've got everything we need to actually write the code, I'm going to take you to the code and show you how to implement. So I'm back again in my workspace. I'm going to show you how we implement the bounding box detector. So I've created an empty class here called bounding box detector. We're going to throw in that standard method as we always do. So that's public static boolean does collide, and that, like always, takes in two entities. We're going to call them primary and secondary. Quickly import the both of them, and for this one we're going to want to make a new method called find axis aligned bounding box. So I'm going to make this public. You'll see why if you keep watching the rest of my videos. If you're only going to be using this class, you're not interested in any of my other collision detectors, then you can make that private. But we do need this information for other algorithms. So I'll check that down there. we start again by taking the vertices. So in my entity class I can just grab the vertices. I'll need to grab the transformation matrix for the entity itself. Maths.create transformation matrix from the entity. If you just do this however you want, like I said at the start, if you don't have a method to do this, then I will include it in my GitHub. Find out what the problem is there. Yep, let's change that to matrix. If I could spell. Finally, we take each vertex, and I'm going to do that as a vector 4f. You'll see why in a sec. And I'm just defining that now so I don't have to keep defining it as I go through. So I'm going to make 6 floats here. So these are the minimum and maximum values for each axial plane. I'm typing quite fast here, but it's worth making sure that you don't have any typos in there. A lot of the problems I was having whilst debugging was I'd have a minimum or a maximum mixed up, like I just did then, and that can really put a spanner in your works. So what I'll do here is I take for integer I equals 0, I is less than the length of the vertices, again divided by 3, I plus plus. You'll see this is very similar to what we were doing before. We do just need to iterate through every vertex here. Equals I times 3, exactly like before. We're going to make the vertex vertices root vertices. So this is literally just loading in the vertex data from the entity to a 4-dimensional vector, root plus 2, and we just set the last one to 1. We then multiply through the matrix 4f. So in LWJGL you can see that as a transform, so transformation by the vertex. This gives us the world space coordinate of the vertex, and this is important. We can't just use the model space because the bounding box takes into account orientation. That's why it makes a more snug fit than the sphere does. So if I equals 0, then this is our first vertex, and we can assume that its min-x is vertex.x, max-x is vertex.x. This means we can instantiate these things. So the reason we can't just go in with undeclared variables is we don't know in world space. Everything could be negative, everything could be massive. It's better to just do it this way, even if it's a bit of a pain to type out. Minimum z is vertex dot z, and maximum z is vertex dot z. Wonderful. So that's if it's our first one. If it's not our first one, then we actually have to do the check. If vertex dot x is larger than our current maximum x, then we set max x to be equal to vertex dot x. I'm sure you can see where this is going, so I'm going to skip ahead. I'm going to copy in a bunch of code for this one so the video isn't obscenely long. All we're doing is we're replacing the maximum and minimum with the next one if they are larger or smaller than them, respectively. When we're done with that, I'm going to return a new float array which just has the minimum x, maximum x, minimum y, minimum Z and maximum Z, and that's the last time you have to type them. Very sorry about that. So that's the axis align bounding box. We have most of the work done for this class now. The only other thing we need to define is static boolean if they overlap. Or more specifically, what we're going to be testing here is if they don't. Array box 2. So this just takes in two axis line bounding boxes. What we do is we check if box 1 is greater than box 2. So just to explain what I've done there, I've checked if the lowest value of x on box 1 is greater than the largest value of x for box 2. If they are, the two boxes can't overlap in world space, so we just return false. I'm going to quickly copy paste that down there, and we need to check that in reverse. So if the if the smallest of box 2 is larger than the largest of box 1, then we also return it. Then we just check the other 3 dimensions. So I do that by 2, 2, 3 and 3, and finally with 4 and 5. So all that's checking is if any situation where they don't overlap occurs, it'll return false. Otherwise, if they definitely overlap on every axis, then we return true. And finally, we make a bounding box for primary box. Bounding box primary. So this is the bounding box for the primary entity. Just copy paste that for the secondary entity, making sure to change the variables and the name here, and we just return intersects primary box and secondary box, and that's it. That is an axis aligned bounding box detector as defined as part of our method. So I'm going to go into the collision detector, make, like we had before, public static boolean box collide, and that's going to take in 2 entities. You'll see there's a lot of repetition here, and we return the bounding box detector I have to change that. Bounding box detect. I'm having a bad spelling day. Does collide primary and secondary. And that's it. So that about does it for this video. Next time we're going to be looking at the hyperplane separation algorithm for some more precise collision detection. Thank you so much for watching. If you have any questions, comments or suggestions, please leave them below, and I'll see you all very soon.